In a 208 volts three-phase system, the voltage from any one of the three phases to the neutral conductor is indeed 120 volts. This voltage relationship arises from the fundamental characteristics of a three-phase power distribution. To understand this, consider firstly the nature of a three-phase system. It consists of three alternating current voltages, each offset by 120 degrees in phase relative to the others. These phases are typically labeled A, B, and C. Secondly, the voltage measured between any two of these phases is referred to as the line-to-line voltage, or simply the line voltage, which in this case is 208 volts. Thirdly, the voltage measured between any one of these phases and the neutral conductor is called the line-to-neutral voltage or phase voltage. The mathematical relationship between line voltage and phase voltage in a balanced three-phase system is described by the equation line voltage equals phase voltage multiplied by the square root of 3. Conversely, phase voltage equals line voltage divided by the square root of 3. In a 208 volts three-phase system, the line voltage is 208 volts. Therefore, to calculate the phase voltage, which is the voltage from phase to neutral, we divide 208 volts by the square root of 3. The square root of 3 is approximately 1.732. Thus, the phase voltage is approximately 208 volts / 1.732, which equals approximately 120 volts. Therefore, the voltage between any phase A, B, or C and the neutral conductor in a 208 volts three-phase system is 120 volts. This 120 volts phase to neutral voltage is commonly used for lighting and small appliance circuits in commercial and industrial buildings that utilize 208 volts three-phase power for larger equipment. This configuration allows for the efficient distribution of power for both single-phase and three-phase loads from the same electrical system. To elaborate further, consider the implications of this voltage relationship in practical applications. In a commercial building, for example, a 208 volts three-phase system might power large air conditioning units, motors, and other heavy-duty equipment. At the same time, the 120 volts phase to neutral voltage provides the necessary power for standard lighting fixtures, computers, and other office equipment. The use of a 208 volts three-phase system with a 120 volts phase to neutral voltage offers a balance between efficient power delivery for high-demand loads and compatibility with common single-phase appliances. It's worth noting that in a balanced three-phase system, the currents in each of the three phases are equal in magnitude and 120 degrees apart in phase. This balance minimizes the current flowing in the neutral conductor. In a perfectly balanced system, the neutral current would be zero. However, in reality, imbalances in the load distribution across the three phases can result in some current flowing in the neutral conductor. Electrical codes and standards provide guidelines for sizing the neutral conductor to accommodate potential imbalances. For example, the National Electrical Code or NEC contains provisions that address the sizing of neutral conductors in three-phase systems, taking into account the types of load served and the potential for harmonic currents. The NEC Table 220.61 provides guidance on neutral conductor sizing. Understanding the voltage relationships in a three-phase system is essential for electrical engineers, electricians, and technicians involved in the design, installation, and maintenance of electrical systems. It enables them to properly select equipment, size conductors, and ensure the safe and reliable operation of the electrical system. In summary, the 208 volts three-phase system provides a versatile power distribution scheme that offers both three-phase power for heavy-duty equipment and single-phase power for general-purpose loads. The 120 volts phase to neutral voltage is a direct result of the inherent voltage relationships in a balanced three-phase system, where the phase voltage is equal to the line voltage divided by the square root of 3. Now let's discuss some specific scenarios and considerations when dealing with 208 volts three-phase systems. Firstly, when connecting single-phase loads to a 208 volts three-phase panel, it is important to distribute the loads as evenly as possible across the three phases. This helps to maintain a balanced load in the system and minimize the current in the neutral conductor. Secondly, if a significant imbalance exists, it can lead to voltage imbalances, increased neutral current, and potential overheating of transformers and conductors. Therefore, it is crucial to monitor the current in each phase and the neutral conductor to ensure that the system is operating within acceptable limits. Thirdly, when installing a new 208 volts three-phase panel, it is essential to follow all applicable electrical codes and standards such as the NEC. This includes properly sizing the conductors, overcurrent protection devices, and grounding system. The NEC Articles 210.19, 215.2, and 250.24 provide guidance on conductor sizing, feeder protection, and grounding requirements. Fourthly, the grounding system is particularly important in a three-phase system to provide a low impedance path for fault currents and to protect against electric shock hazards. The grounding electrode system should be properly installed and connected to the neutral conductor at the service entrance. The NEC Article 250 covers the requirements for grounding and bonding. Fifthly, when working with 208 volts three-phase power, it is essential to follow safe work practices and use appropriate personal protective equipment or PPE. This includes wearing insulated gloves, safety glasses, and arc-rated clothing. Always de-energize the circuit before working on it and verify that it is de-energized using a voltage tester. Sixthly, when troubleshooting a 208 volts three-phase system, it is important to use a multimeter to measure the voltage and current in each phase and the neutral conductor. This can help to identify any imbalances, voltage drops, or other problems. Also, an insulation resistance tester, also known as a megometer, can be used to check the insulation resistance of conductors and equipment. Seventhly, it is important to understand the different types of three-phase transformers that are used in 208 volts three-phase systems. The most common type is the delta Y transformer, which has a delta-connected primary winding and a Y-connected secondary winding. This type of transformer provides a neutral point on the secondary side, which is necessary for supplying 120 volts phase to neutral loads. The NEC Article 450 covers the requirements for transformers. Eighthly, harmonic currents can be a significant concern in three-phase systems, particularly in buildings with a large number of electronic devices such as computers and variable frequency drives. Harmonic currents can cause overheating of transformers and conductors, as well as interference with other electronic equipment. Filters and other mitigation techniques can be used to reduce harmonic currents. Ninthly, surge protection devices or SPD should be installed on 208 volts three-phase panels to protect against voltage surges caused by lightning or other events. SPD can help to prevent damage to sensitive electronic equipment. The NEC Article 285 covers the requirements for surge protection devices. Tenthly, regular maintenance and inspection of 208 volts three-phase systems are essential to ensure their safe and reliable operation. This includes checking the tightness of connections, inspecting conductors for damage, and testing the operation of overcurrent protection devices. In conclusion, understanding the characteristics of 208 volts three-phase systems, including the 120 volts phase to neutral voltage, is crucial for anyone working with electrical systems in commercial and industrial buildings. By following safe work practices, adhering to electrical codes and standards, and performing regular maintenance, you can ensure the safe and reliable operation of these systems. In a 208 volt system, remember that each of the three phases is 120 degrees apart. When measuring voltage, the line-to-line voltage, meaning from one phase to another, will measure 208 volts. The voltage between any one phase and neutral will be 120 volts. The neutral conductor serves as the return path for current from single-phase 120 volts loads. These loads are connected between one of the phases and the neutral conductor. Balancing the single-phase loads across the three phases is important. This helps to prevent excessive current in the neutral conductor and ensures that the three-phase system operates efficiently. Unbalanced loads can cause voltage imbalances. This can lead to overheating of equipment and reduced efficiency. Regularly inspect the electrical panel and connections. Look for signs of overheating, loose connections, or corrosion. Tighten any loose connections to prevent arcing and potential fire hazards. Consider using a thermal imager. This can help to identify hot spots in the electrical panel.